Bismillahirrahmanirrahim. I am Dr. Muhammad Adnan, working as Assistant Professor in the Department of Physics, Kohat University of Science and Technology. I welcome you to the course PHY 352 Nuclear Physics 1. Today it is the 19th lecture of this course and the topic is Deuteron. First, I will give the learning objectives. At the end of this lecture, the student will understand the concept of nucleon-nucleon interaction in the nuclei deuteron. In this course, we are following the book Introductory Nuclear Physics by Kenneth S. Crane, 3rd edition. In this lecture, I have taken some of the illustrations from this book. Since in this part of the course we are now studying the nature of the nuclear force and we have discussed some introductory remarks regarding the nuclear force and the nature of the nuclear force, today we will be discussing how nucleon interact through this nuclear force, but we will be just seeing how the potential associated with the nuclear force varies with R. That is, in this lecture we'll be studying deuteron, which is H2, that is a nucleus having two nucleons, consists of a neutron and a proton. A neutral atom of deuteron is called deuterium. That is, the nuclei are known as the deuteron, and the atoms, or we can say once we are talking about atomic physics, then it is deuterium. So we are studying the nucleus of this atom H2, that is, it contains two nucleons, one is proton and the other one is neutron. And we will see how they interact with each other through that nuclear force, or we can say how much is that strength, since it is difficult to describe the potential associated with the nuclear force, since in the last lecture we have also discussed that the potential, or we can say the nature, is complex to analyze at this level. It is the simplest bound state of the nucleons and therefore give us an ideal system for studying the nucleon-nucleon interaction, since this is the simplest case, having only two nucleons. So that's why this is the simplest case, and an ideal system like in atomic physics, the state of hydrogen atom is the simplest, or we can say the ideal system, studying the interaction of, in that situation, the interaction between the nucleus and the electrons. So here we have a deuteron, that is an ideal system whilst for studying the nucleon-nucleon interaction. Just as a measured Balmer series of the electromagnetic transition between the excited states of the hydrogen led to the understanding of the structure of hydrogen, so should the electromagnetic transition between the excited states of the deuteron lead to the understanding of its structure. So there's a question whether, as I told you, that it's an ideal system like the hydrogen atom, but there the hydrogen atom have several excited states, but unfortunately once we are talking about deuteron, that is having one proton and one neutron, there is no excited state inside, and the only unbound the excited states are the unbound system consisting of a free proton and a neutron. That is, once you give energy equal to the binding energy of deuteron that we will be discussing in this lecture, then there are no excited states available for these nucleons, so that the same mechanism can be applied as in the atomic physics for the hydrogen atom. So the various parameters that is well tabulated regarding the deuteron, that is, deuteron consists of one proton and one neutron. The mass is 2.014 in atomic mass unit. The binding energy is 2.2 mega electron volt. And the interesting thing is that deuteron do not have any excited state. So before we start with the interaction potential, or we can say the study of the interaction potential, we'll be discussing just a recap of what you have done regarding the binding energies. So the first thing is how to calculate the binding energy of this deuteron, which I have shown that it is around 2.2 mega electron volt. So the first method that is given is the mass doublet method, in which you calculate in the first part of the course it is there. Once you calculate this mass, and then you can use that mass, the atomic mass, so that you can find out this binding energy, as we have discussed this in detail in lecture number 9. Now the second procedure through which you can find out, or we can say verify this binding energy, which is 2.2 mega electron volt, is measured energy released by gamma rays on the formation from a neutron and proton. That is, if one brings the proton and a neutron close together so that it fuses to a deuteron, and the energy released in the form of gamma rays will be having energy equal to 2.2 mega electron volt. Similarly, proton dissociation is another way to track this energy, that is 2.2 mega electron volt. That is, if we want to dissociate this deuteron into a proton and a neutron, so for that this gamma must have an energy 2.2, so that it dissociate it into proton and a neutron. So there are binding energy which is around 2.2 mega electron volt. That is one parameter we'll be using in our discussion today. So the binding energy is 2.2 mega electron volt. Now, if you remember, once we were discussing the semi-empirical mass formula, so there we concluded that the average binding energy per nucleon for a typical nuclei is 8 mega electron volt. So the deuteron is therefore weakly bound system compared to those typically nuclei, since the binding energy is 2.2, so that we can say that deuteron is weakly bound. So if you want to compare this 8 mega electron volt for the binding energy per nucleon, so deuteron is having 2.2 mega electron volt, and there are 2 nucleons. So this number for the deuteron will be 1.1 mega electron volt, since in deuteron we have only 2 nucleons, so the binding energy per nucleon will be 1.1. So if we compare that 1.1 mega electron volt energy for the deuteron per nucleon to 8 mega electron volt for a typical nuclei, so we can say that deuteron is a weakly bound system. Now, in order to study the interaction of this weakly bound system, which contains one proton and one neutron, we need to analyze our discussion based on a three-dimensional square well potential. That is, the interaction between proton and neutron inside the deuteron nuclei is due to the nuclear force, and that associated potential, as I told you, is complex to analyze at this level. So we assume that that potential is of the form as shown here, that is a three-dimensional square well potential. That is, that once the nucleon, that is a proton and neutron, are let's say on this axis we are having R parameter, which is the separation between the two nucleon, which is proton and neutron. Once they are, let's say R is equal to capital R, which is the measure of the diameter of the deuteron. So once they are inside those diameter, or we can say the separation between the proton and neutron is less than the diameter of the deuteron, then they will be interacting with a nuclear force, and the associated potential is, we assume that that it is of this form, that is it is minus V naught. So the depth will be will reflect the strength of this force. So we are just representing it by minus V naught. Once the deuteron nuclei, in which we have one proton and one neutron, are separated by a distance more than the diameter of the nuclei, then they will not feeling that potential, which is due to the supposed potential due to the strong nuclear force. So we will see at the end that this is around 2 femtometer. So once we can say that once the two nucleon, proton and neutron, are at a distance less than 2 femtometer, roughly speaking, they will be interacting through that potential, or we can say they are influenced by that potential, which is the potential associated with the nuclear force. Now this line is representing the binding energy. As we have discussed that this is weakly bound system, so just analyzing that it is very small, that is around 2.2 mega electron volt. Since this is binding energy, so we are showing it on the this below line. Now this is of course an oversimplification, that is representing the potential associated with the nuclear force by this three-dimensional square well potential, and that varies only with R. This is an oversimplification. If you remember that in last lecture we have discussed that the nuclear force depends upon the non-central tensor component as well. That is, it depends upon the spin orientations and all those things. In last lecture I told you that the nuclear force do not lie along the line joining the two nucleons, or rather we can say that there is a non-central component as well. So we are assuming this just to understand the strength of the nuclear force, so that we have simplified that this potential is let's say spherically symmetric, that is a central potential. So that central potential, that is, this potential exists once R, which is that parameter, the separation between the two nucleons, are less than that the size of the deuteron. So once the separation between the two nucleons is smaller than the size of the deuteron, so they will be connected by the potential which we assume that it is of the square well form due to the nuclear force. And once the separation between the nucleons is greater than R, which is the estimate of the size of the deuteron, that is as I told you, around 2 femtometer. Once they are more than 2 femtometer apart, then they will not be feeling that potential. So this is the potential associated, that is our modeling to understand the strength of the nuclear force, that is the interaction between a proton and neutron inside a deuteron. Now, as I told you, this R represents the separation between the proton and the neutron. So R is in the effect of the measure of the diameter of the nucleons, as I told you. Beyond the size, or we can say after that, this is not experience, or we can say there will be no force between the nucleons with respect to that strong nuclear force. Now, how to model now this interaction between the proton and neutron, that can be done with the help of the Schrödinger equation. That is, we will be writing the equation for that two nucleons interacting through a potential of this kind, as we have assumed that it is the form of through which they are interacting. So the standard procedure is that we need to write the time-independent Schrödinger equation, that is H psi equal to E psi, and then in the H we need to write the operator form, that is the kinetic energy and the potential energy, which is split into two forms. Another thing is that this potential only depends upon the radial component. So that will make our a solution to this differential equation, or the Schrödinger equation, simpler, since once we are talking about central potential, so that the potential depends upon only the radial part, and the, let's say, in spherical symmetric potential, the phi and theta will not affecting the nature of this wave function, but rather those will be constant. That is, if we have a spherical, almost a spherical nuclei of Deuteron, in which the two nucleons, proton and neutron, are interacting through that potential, which depends upon only R, that is on either side, whether theta and phi changes, but once the separation is fixed, the potential will be the same V naught, and irrespective of theta and phi. So that is the assumption which we have simplified for our analysis, that assuming that the potential, or we can say the potential associated with the nuclear force, is central. So we need to solve this equation based on this potential well analysis. That is, this was the Schrödinger equation. Assuming central potential, then the wave function solution can be separated into radial and angular parts. So as I told you, you have already done these things in your quantum mechanics course, that once you are solving this Schrödinger equation for a central potential, that is, the potential do not depends upon the various orientations, or we can say different theta phi will not affect this potential, so that then we can split the solution into radial and angular part like this. So this function, wave function psi, will be having a radial part which will determine actually the energy, and this will be fixed. You also learned this in your quantum mechanics code, that this is the spherical harmonics. So for a given L and M, this will give you a constant value. So you will see on the coming slide that once we are talking about Deuteron, as at the beginning I told you that Deuteron do not have any excited states. Very light, weakly bound state. So once we are saying that there are no excited states, so this L will be 0, and we know that the M value is in between minus L to plus L, so this will be 0, and this will be L is equal to 0 means the lowest energy state, or we can say the ground state. Once we have only state in the Deuteron, or we can say in terms of energy states in the Deuteron is the ground state, which is the lowest energy state, and that will be L is equal to 0. So why am I discussing it here, that this part will give us a constant value. So we need to just solve this part, and at the end this is well tabulated values. So we'll just put L is equal to 0, M is equal to 0, and that will give you a constant value, and that will be the solution. So we need to concentrate on this radial part, which is the part which actually changes the energy, or this is the fixed part. So in order to solve such problem based on the Schrödinger equation, that we need to split the radial and angular part, and it is handy to write this radial part in terms of a parameter u divided by r into the Schrödinger equation. Then this u of r satisfies the following equation. That is, we need to put that over here. That is, in another word, we need to transform this psi into u, so that these are just 3-4 steps. You need to write this L into L plus 1 h cut square divided by 2m square. Now you need to just use this expression and transform this psi into u. That is the representation of the radial part. So instead of solving it for the complete 3 coordinates r, theta, phi, these theta and phi are not affecting the potential associated with the nuclear force that we are assuming to be square well, so that we need to just concentrate on this part, and so we just use this thing. As I told you, since in the beginning I told you Deuteron do not have any excited states. So for that situation, the ground state is the lowest energy state, and that corresponds to L is equal to 0. So if we put this L is equal to 0 here, so that this solution, which will be the solution of the radial part only, the other part is just constant. So that if we make this equal to 0 by taking L is equal to 0 in this expression, which arrives because we need to transform that into this form. So we have these two equations are actually the same Schrödinger equation, but the radial part. And as I told you, that potential is shown here, is having a form when r is less than r, this is minus v naught, and when r is greater than r, so this is 0, as described by this diagram. So in that way, the radial part, or we can say once this is 0, we need to put this v of r equal to v naught for r less than capital R, and then when this Vr is equal to 0 when R is greater than R. So these two expressions are just this is the same equation, but we just put the value of the potential that we assume to be V naught once R is smaller than R, and this is 0 once the separation is greater than the size of the Deuteron. So we need to solve this radial part of the Schrödinger equation for these two regions. So that is our goal in this lecture. That is, we have the same diagram in which the potential is of the form given by minus V naught once R is less than the size of the Deuteron. So that was the first equation. So we need to solve this. So this was the situation. We are solving the Schrödinger equation for R less than R, and remember the theta and phi part are constant. So this is the equation which we have rearranged just to multiply these things across the equation, so that just define this K1 such that this K1 is a positive number, so that if we just know from your differential equation course, you know that the solution of this will be sinusoidal. That is, once this is a positive quantity, this E naught plus V naught divided by 2H, so that this solution of the radial part of the Schrodinger equation is this thing once R is smaller than R. That is, inside the wave function, the part of the wave function, or you can say the radial part, is of this form. Now we need to use the finiteness of the wave function. That is, the wave function should be finite. That is, once R goes to 0, so that this U or this will be you see, this will be 0. That is, this wave function should give you 0 once this R goes to 0. Now if we just put you can say this U equal to 0 by putting R equal to 0. So if we put this in this equation, R equal to 0, so this function will give you 0 and this will give you 1. So that means that this B is 0. That is, the coefficient B must be set to 0. Therefore the acceptable solution of the physical meaning is given by this A cos 1 of R. These are two parts. So the finiteness of the wave function requires that this should goes to 0. The U should go to 0, so that this which is the as if you remember the radial part of the wave function, we have described it in terms of U over R. So if U goes to 0, so in that regard this wave function will be going to 0. Otherwise, when R equal to 0, if this is not equal to 0, so this will go to infinity, which will violate the condition of the finiteness of the wave function. So we need to make things on record before moving forward in this lecture. The first thing is that we have obtained the solution of the Schrodinger equation for the radial part in this region, that is, once R is smaller than R. So this is the first solution. So we'll use this solution later on. Now once R is greater than R, that is, the potential was 0, so in that situation the radial part of the Schrodinger equation takes this form, since the potential is 0 once R is greater than the size of the Deuteron. Again, we need to rearrange this expression and defining the K2 now, which is again a positive number, since this minus and this E, which is the binding energy, which is negative. So overall this will give you a positive quantity. So once we have this K2 positive and there is a negative sign, so that means that this solution is of this form, which is the exponential. So U in this case is exponential. So we need to make this physical by again using the finiteness condition of the wave function. That is, for R goes to infinity, so we have these two solutions. Now when R goes to infinity, this U should go to 0, because this should go to 0, because as I told you, this K2 is positive. So when R is very large, so this will decay, this will go to 0. And what about this thing? Again, this is positive, K2 is positive. So when R is very large, so this is a growing solution. So once this is infinity, so that means in that situation this thing will go to infinity. But as I told you, the finiteness requires that this should go to 0. So we need to make this D coefficient equal to 0, so that the physically acceptable solution will be like this. So in order to make the wave function finite, this part needs to this is not physical, because when R is very large, this term is going to be very large. So in that regard, this u, which is the radial part of the wave function, that will also be very large. That is, it will be no more be finite. So that means that we need to make this d coefficient equal to 0, so that we left with only the physical solution, that once r is very large, so this exponential factor will make the u finite and it will converge to 0. So this is the second solution, or we can say once r is greater than r. So you see that potential, or the radial the wave function, the radial part of the wave function, once this is greater than r, it is exponential. So inside, in the first part, we have seen that the solution of the Schrödinger equation was sinusoidal, and once we are at a distance, or we can say the Deuteron separation is more than this capital R, that is the effective diameter, which is around 2.1 femtometer. So once the Deuteron are separated more than 2.1 femtometer, then the wave function is exponentially decaying. So if we just make the radial part in two ways, so we have solved the radial part of the Schrödinger equation in these two limits. In the first limit, the solution of the radial part gave us a sinusoidal solution, and in the second, it was the decaying solution. So we have these two solutions in these two limits. So we need to find out, since we are interested to know how much, or we can say how much is that potential, which is the interact, and which we suppose that this is of the form of potential between the nucleons through which they are interacting through the force, the nuclear force. So we need to find out that. So for that, we need to apply the continuity condition on this u and derivative of this u with respect to r at r equal to 0. That is, again, you learn this in quantum mechanics, that the wave function should be continuous, and also their first derivative at the boundary should also be continuous. That is, the slope are also consistent and the function are also consistent. That is, we have a boundary at r is equal to capital R. Beyond this side, we have one solution, and once r is greater than r, we have another solution. So this continuity means that at this boundary, you take this solution or this solution, the two will be the same. So that is the continuity requirement for the wave function. Since this u, remember, this u is part of the wave function, the radial part of the wave function. Now, the first condition of the continuity, that is, we at r is equal to r naught, if we just put r is equal to r naught, this will be a sine k1, and this will be capital R. So at r is equal to capital R, that is the boundary, the two solutions are equal. Whether you are using this solution or this solution, the two will be the same. So this is the continuity of the wave function. Now the second continuity requires that we need to differentiate this, and you need to equate once r is equal to capital R. So we need to differentiate this wave function, that is a sine of k1r. So in that regard, differentiating with respect to r, so there will be k1 here. So the derivative of this first solution, which is at the boundary, k1a cos of k1r equal to, since we need to put r is equal to r, so that boundary equate them according to the conditions. And we need to differentiate this again with respect to r, so that there will be minus k2, and then c and the same exponential factor. So the equation 1 arises because of the continuity of the wave function, and this equation 2 arises because of the continuity of the first derivative at the boundary, which is r is equal to r. So these two conditions, the continuity condition, give us this solution. As I told you, we are interested to know the strength of this potential, which is the associated potential with the nuclear force. So we need to just divide this 2 by 1 so that we have this transcendental equation, and we know the definitions of K1 and K2 we have defined for while solving the radial part of the Schrödinger equation in the first region, and in the second region we have this definition. So if we just use this equation in this final solution, which arises because of the continuity condition of the wave function and the derivative, so that we will be having this transcendental equation give us a relation between the V naught, which is the potential in which we are interested to know the strength of this potential, and the rest of the parameters you see in this equation. This R, as I told you, this is around 2.1 femtometer. In this K we have energy, this is 2.2 mega electron volt. At the beginning we have discussed this is unknown, this H cut is known in the second. So we have this M. Remember, this is important, that this M is not mass of the nucleon, but since we were working in the relative coordinates, so that this R is the separation, so that this M will be the reduced mass, which will be equal to this M is equal to MP multiplied by Mn divided by Mp plus Mn, where Mp is mass of the proton and Mn is the mass of the neutron. So that make the mathematics simpler while working in the reduced mass situation, since we are making this R as the separation between the two nucleons. The transcendental equation, as I told you, all the parameters are there, but this is not that simple to solve, since transcendental equation often do not have a closed form solutions, but they can be solved to using the computers to obtain. Since we have only one equation and we have only one unknown, but the equation is complex, so that it is not that easy to solve, but using the computer one can manage to solve this value of this potential, which is the square well potential that we assumed for the nuclear force. Since this is known now, this is 2.2 mega electron volt, H cut is known, so this R is 2.1 femtometer. So as I told you, this is one equation and one unknown, which is V naught, so that the strength of the potential associated can be feel, at least, since we have simplified our analysis by taking few assumptions, but still this will give us a nice way to understand this value. Now, for electron scattering experiment, the average radius is 2.1 femtometer, as I told you, the capital R, so that this potential can be worked out, and this is a large potential, that is 35 mega electron volt potential associated with the nuclear force through which they are interacting. Now, as I told you, this is 2.1 femtometer. So if we use these parameters in the last equation, one can find out, as I told you, this is a difficult equation, the transcendental equation, but one can manage to obtain this value, which is around 35 mega electron volt. So we can say that the bound state of the deuteron at an energy of around 2 mega electron volt is very close to the top of the well, and that's why it's a loosely bound system. But inside, since the deuteron do not have any excited state, so this is the only available ground state for these nucleons. Now, if we just use the graphs, so if we make this V is equal to minus V naught, the potential which is at R is equal to R exists, and beyond that the potential is not there. So if we just if you remember on the last few slides, we have discussed the continuity of the wave function. So this U of R, which is the solution of the radial part of the Schrodinger equation inside that well. So inside that well, one r is less than capital R. So this is that the solution, the sinusoidal solution. You can work out more on the detail why this is 1/4 part of this, since beyond that in that solution the other side is negative. So to make the continuity of the solution of the two solution, so that they are just continuous across this boundary, so that there is no hiccups. You see, the one solution joins the second one in a nice way, so that beyond r is equal to capital R, we have this exponentially decaying solution. And on this side we have the sinusoidal solution. As I told you, you can work out the various aspects now, why this is 1/4 and all those things. This is the bound, the single bound state, which is 2.2 mega electron volt in energy, and beyond this there is no potential associated. So once R is in 2.1 femtometer, this potential will be experienced, which is a huge potential, and the deuteron is having one bound state. Next we will be discussing the various parameters regarding the deuterons once we start with the next lecture. So with this, I thank you for